Hey you guys, welcome back to the channel PHYSICSSIRJEE, and here we are in PHYSICSSIRJEE Originals, and I've brought forward to you, as promised in the previous video, another question from the Physika's round 1 that was held on September 5th, 2021. Okay, so this was a question on mutual inductance. It had multiple layers to it, so all the concepts within the JEE Advanced makes it a very intriguing video, and also some of the unseen methods would be explored in this particular video. Also, at the end of the video, we'll top it off with 3 very important practice problems at varying difficulty levels, all for the JEE aspirants. Okay, so I hope you're excited. So am I. So let's move ahead with the problem statement. For those who have not attempted that exam, I would request you to pause the video here and give it a try for 5 to 10 minutes, and do come back for the concept solution and the practice problems at the end. Okay, so here are the 4 options that are given. So one or more than one might be correct. Okay, so I'm going ahead with the formal reading. The self-inductance of a equilateral triangular loop of side L shown in figure 1 is capital L. A rhombus of one internal angle 60 degrees and side L, which is shown in figure 2, is placed very close to triangle so that one of their sides align as in figure 3. Okay. Now, what you're talking about is that if the loop in figure 1 was of the side twice the side that is given in figure 1, then the self-inductance is 2 times. The self-inductance of loop in figure 2, that is the rhombus, is greater than 2L. The mutual inductance between the two loops is in figure 3, L by 3. And in the 4th option, he's giving us a choice that the mutual inductance in figure 3 is supposedly 4L by 3. Okay, so I hope you understood what we are doing here, and let's try to solve the problem based on the concepts that we'll start off with. We'll first attack the first option. Problem has been smartly designed in such a way that is what JEE Advanced also does in more than one correct type, right? Most of the times, one of the options would be the hint in towards the thinking of the other option. So that's how this has been designed. So let's try to explore that. Before I do that, I would like to bring to your notice that our beloved website has been updated again. For all the videos chapter wise and series wise from this channel are put up in the website all over again. Okay, so this is done so that in the last 1 month of the JEE advanced preparation, for the old subscribers, also the newbies coming into the channel, they'll have a very comfortable quick revision before going into the exam. Okay, so do check out the PHYSICSSIRJEE.in website. Okay, so you'll understand what I'm talking about. Okay, right. And also one small request as always, right? So please make sure you give it a like to this video. The liked videos get propagated and increase the reach of the channel. So the target is as simple as every time. So 750 likes for this video. I'll come up with another important video for your JEE preparation. So I hope you'll do that. You have been doing that, and thanks for all your support. Please keep extending the support. And for the first option about the double the size of the triangle, you will use dimensional analysis. Okay, so if the loop of current I was having a side L, it was already given the mutual inductance, sorry, self-inductance was capital L. So magnetic field due to the triangular loop at any point inside, right? So at a symmetry point somewhere here, we can easily find. At all other points also we are able to find, but we're not interested in the calculation. We are interested in the proportionality with the length. Okay, so I think by using Biot-Savart law and some guesswork, you should be able to realize that we can write the magnetic field at any point somewhere here, let's suppose, as a factor of that factor, let's say, is gamma of mu naught current divided by L. If current I is flowing and L is the side length, you should be able to write this as mu naught I by L times of gamma. Now, what's this value of gamma? Yes, it will depend on which position you're talking about. So we all will agree that gamma is a position dependent quantity for all points inside the triangle. Now, how do you calculate the self-inductance? You'll first calculate the self-flux linked with the triangle. So whatever this B factor is there, that you take dot product with small areas inside this and you integrate. So gamma stays inside, gets integrated, but spits out this L, and it will end up coming out to be proportional to L. Why is it coming out to be proportional to L? Please understand that the area will be proportional to L square in the numerator, and there is a 1 by L here. So this dot product comes out to be proportional to L. Whatever happens to gamma is immaterial. It is dependent only on the shape, which means if this size of the triangle has become 2L, that is the side has become 2L, then this would become 2 times with the gamma factor remaining the same. So the self-inductance of the triangle of the side twice the length should be twice the self-inductance of the smaller triangle. So this is one option that will lead us to thinking about the last two options. So let's move ahead. So before we introduce basics of mutual flux, most of the JEE aspirants would be knowing this, but just to refresh, if you have one coil carrying current in which the current is changing, the flux of this change can be recorded in another coil. Even if the current in the coil 2 is 0, we can actually have a mutual inductance related flux. Okay, so and that flux, if it varies with time, there is a EMF induced. Okay, so this is what the picture depicts. The value of that mutual inductance of 1 due to the changes in 2, or of 2 coil due to the changes in 1, both will be equal to each other by the theorem of reciprocity. Okay, so that's why we need not even write the subscripts here. So the value of mutual flux here, how do you read this? Phi 2 1, mutual flux of 2, that is in coil 2, with respect to 1, that is due to the changes in 1, is equal to the same capital M into I1. The changes were made in 1, so you take the current in I1. Also, the self flux in coil 1 itself, you can write as the double subscript 1, or people prefer to write as phi 1, is L1 I1, that is in this one, the self-inductance L1 and the same current in itself. And the mutual induced EMF in this one is the differentiation of this with respect to time. So this would be M di1 by dt. If current were running in coil 2 and that was changing, it could induce a mutual flux in coil 1. That also we can write. So these are the basic formulae that people should be knowing before we move on. Okay, so I just wanted to introduce that. So now let's build up the third figure. So let's go back to the question to refresh ourselves. Okay, so you see this in the third figure, this rhombus, which was having an internal angle of 60 degrees, 4 sides equal, can be divided into 2 more equilateral triangles of this kind. So when someone has placed this triangle and this rhombus together, you can actually cut this rhombus into 2 more equilateral triangles and draw the figure that I'm going to show. So I hope you can visualize this diagram into this slide. Here we are. Okay, so to look at the left one. So the bottom rhombus is now amalgamation of 2 equilateral triangles. Okay, now what does it mean by calculating the mutual inductance of the top triangle and bottom rhombus? Okay, so let's try to understand that. So to understand that, we'll build up some important mutual inductance terms here. So upper triangle and this triangle share a common side, and therefore I'll define a mutual inductance between these two as M adjacent. These are 2 adjacent triangles which share a side. Okay, even these 2 triangles, which are actually part of the rhombus, share this side. Okay, so if the current were flowing here in the rhombus, I could have cancelled it in this manner. So just look at this one, I'll erase it. So look at the bottom left corner. So if current were flowing like this, actually in the rhombus here, it will flow like this, right? And it will not flow in here. These 2 wires were created by us. So what we are effectively assuming is there is a current flowing like this and a current flowing like this, which cancel each other when we merge the 2 triangles, and it becomes the original rhombus. So that's the you could say idea behind dividing it into 2 triangles. Okay, so now coming back to the logic that I was trying to focus upon. So these 2 triangles are sharing one side. So I define a mutual inductance term as M adjacent. These 2 triangles share an M adjacent, whereas these 2 triangles don't share a side. They're far away from each other. So I'm defining, if at all any mutual inductance is there, then it is M away. What is this mutual inductance? If current flows in this, the flux lines or the field lines go out of the board and go into this triangle and affect the EMF in this. To write that EMF, the M term that I used in this triangle due to the changes in this is called M away. That's the whole logic. So to exploit the symmetry, we divided the bottom rhombus into 2 equilateral triangles. It was made possible because the rhombus was given as a 60-degree internal angle. Okay, so let the mutual inductance be M adjacent and M away as shown in the figure. Now what we need to solve? We need to solve for the mutual inductance between the top triangle and the bottom rhombus. bottom rhombus itself is made of two triangles. So it is equivalent to having this M adjacent and this M away. Right, the upper one interacts with the lower thing in two terms. One is M adjacent and one is M away. This M adjacent is an internal matter of the rhombus, so we'll not include this. So our logic is to solve for M adjacent plus M away. I could write plus because the field lines associated with M adjacent and field lines associated with M away would be of same direction. You can draw the currents in clockwise direction in all the loops and check it out that these two M, when written, see, mutual inductance is always positive. The flux direction or the EMF direction, you have to associate a plus or minus sign when you're writing the equation. Okay, so in that equation, I'm claiming that these two will serve as additions of each other. That's why I could write a plus. Okay, so with all these things built up, let's now use the symmetry argument. So the idea of the first option where the side of 2L, right, had a inductance of 2L, self-inductance, will be used here. You could see this red part of the diagram was same as the previous slide. I smartly snuck in another small green triangle to make it a bigger equilateral triangle. So if the student had got this idea in the exam, problem is done already. So we build an extra triangle, taking the hint from the option A, and make that triangle into a 2L sided triangle. So which means if I were to draw these currents, you could see all clockwise currents. If I draw and merge these triangles, you could see these sides cancel off their currents, right? These sides cancel off their currents. So it's all about this red, and red was originally given. This green triangle was drawn extra to exploit symmetry and scaling. Okay, so just to give you an idea, so the bigger triangle is this one. So what I'll do is I'll make all the internal calculations on one hand and equate it to a bigger triangle's contribution. So that's what we are going to do on the right side with the calculations. Now that you can visualize that this is a bigger triangle, I'll remove this one. Okay, and let's go ahead and account for the flux. Now, I have labeled outer triangles, outside ones, as 1. Can you see the letter 1? And I have taken the middle triangle as the label true. Okay, right? And I'll count all the flux contributions amongst themselves by self and mutual. So all the labeled 1 triangles, you could see this one, and this one. How many self terms each of them will have? Due to a current flowing in them, the self terms would be L1 LIs. Any self triangle will have only one self flux called Li. So this one Li, and 3 such triangles are there. So 3 LIs will be there, where L is the self inductance of one small triangle that was taken at the start. Now, how many mutual terms will this labeled 1 triangles will have? Can you see this one will have a mutual flux with this one, adjacent one, and 2 mutual fluxes with the away ones. This 1 and 1 are away, and this 1 and 1 are away. So when I'm counting the mutual fluxes, it will be 1 M adjacent I and 2 M away I's. And please remember all these numbers, there'll be 3 such ones because you have 3 such labeled triangles. Now coming to the labeled 2 triangle, how many self flux terms will be there? Only 1 Li. How many mutual terms will be there? There will be 3 M adjacents. Can you see? That will be there. And there is no M aways, right? This one doesn't have an away triangle to share. But only one such label 2 triangle are there. So if you are counting all the flux interactions of this entire set, you will have 3 times of this Li, 3 times of these 2 terms, and 1 time of this and 1 time of this. Just add all of this properly with this multiple 3, you will get this LHS. So if you were taking all the interactions, selves and mutuals of this entire big figure, then you'll get 4 Li plus 6 M adjacent I plus 6 M away I. And that should be equal to the big triangle's contribution, which we already said is 2L, right? Into I. Now here comes the important part. All of this I wrote plus, assuming the fluxes are aiding each other. And this mathematical equation also throws one more important light, that these mutual inductance fluxes would be opposing the self flux. And that is very easy to see. If you have a clockwise current, the field lines go in, but by the time they interact with this loop, they actually come out. So this one tells you that these terms should have been minus. Anyway, the value we wanted was the mutual inductance only. So we'll take a modulus for this. But if I had asked flux values, then I would have to solve using a minus sign. Okay, mutual inductance is always positive. It's the flux or the EMF that can have a sign. Okay, so you rearrange and you wanted M adjacent plus M away, it comes out to be L by 3. So keeping that also in mind, you realize that there was one more question that was asked. That was the self-inductance of the rhombus itself, only rhombus part, is it more than 2L or less than 2L? You can go ahead with the same logic and say that the self-inductance terms will add up, that is 2L, but the mutual inductance terms will actually subtract because M's oppose L's in these two triangles. So we also got an idea to solve for the second option, and that would be that it is less than 2L and not more than 2L. You could see this greater than 2L would be a wrong option. Let me mark it in red. Yeah, this one should have been less than 2L. Okay, so keeping all these things in mind, the correct answers are A and C in the exam. Okay, so I hope now you're ready for the practice problems. Now in the practice problem, what I'll do is I'll try to give you a problem in which the sign is also important. Here, even if you made a mistake with the sign, you could have actually gone ahead with the correct answer, right? So before I do that, I would like to bring an attention to you about the EMI and AC playlist. All the subtopic wise playlists are given in the description below. Right, I think I made it into 5 subtopics to suit the needs of a JEE advanced aspirant. So each of these, play them in order before you reach the final examination. To just bring to your notice another important thing, within this playlist, I have already made 2 important mutual inductance or mutual flux problems. One is from the iridos superconductor, where a lot of, you could say, solutions that are there in the public domain slightly write wrong methods and finally get the right answer because maybe some mistakes were done twice and the cancellations were done. So this left side video throws light upon the intricacies of how to do it using torque and energy methods both. And also as a practice problem of this one, I have solved another problem. Even though it's an Olympiad workout series, the type of challenge that is posed in this right side video gives you more insight into the mutual inductance. And also one more important thing, as some users pointed out in the right side video, I made actually an error with the sign in the final step. Like in this video, that sign did not cost me to the final answer. So that motivates me. If a teacher can also, if not very careful, can make a sign mistake in mutual flux, students should be even more careful. So with that as the agenda, right, once you see the video, you'll understand this. The practice problem number 1 has been made, keeping that in mind. Okay, so this is the practice problem 1, where you cannot get away with the wrong assumption of the sign. So this I'll answer in the PHYSICSSIRJEE quickies. Okay, so there is some description of the situation. Loop 1 is this and loop 2 is in the same plane away. Mutual inductance is M. I1 is given in this direction. So sign of these terms will also be important. So 4 options for the modified Kirchhoff's law, along with the none of these is mentioned. So comment your response along with the timestamp. It's important so that I can comment back. Okay, and problem number 2 is again an original problem, even though this is actually modified version of a previous Olympiad question, right? And what I did is I modified it to be a JEE advanced list A matching type question. Okay, so try to go through this. There is some scaling and symmetry arguments that you can utilize here. It's a very good problem, and try to match the column 1 to column 2 with the options below. Okay, so please do respond with the timestamp. I'll come up with the solutions in the PHYSICSSIRJEE originals. And the last one is also an interesting one. Problem number 3 recently appeared in one of our AITS examinations. Okay, so China AITS, and this is a problem which couples mutual inductance with AC chapter. So slightly tricky question. Is one or more than one maybe correct type. So again, respond with the timestamp of this question so that I can comment back whether you're right or not. I'll answer it in the AITS select series. All these series that I'm mentioning, the links of these ones are given in the description below. Each one has multiple videos which cater to the needs of the students. So I urge you students to go through them. If you don't want to wait for my solutions video ones because it takes time, you want to have immediate discussions, immediate answers for these beautiful questions and many more, please do join our Discord server, which has already crossed 2K valuable subscribers. Real aspirants, I should say, right? Not the ones who just float around in YouTube for fun. Okay, so there are separate channels for each topic, less like EMI and AC channels are there. Do check out. And if you're new, what is Discord and all that, I have made a video tutorial. Just that video link is in the I button above or the description below. Watch it, join, just check it out how good the server is maintained and how many important problems get discussed by students there. You'll understand it's a gold mine. Okay, so and apart from that, in this particular channel itself, there are parallel series that cater to the needs. So I've written only 4 series. There are many more. Just try to explore them in the description, and try to watch 2 or 3 videos every day till the JEE advanced exam comes closer. For every video, you will start getting some insights that you don't get in books in this particular channel, which adds to your exam oriented approach. That's very, very important, and I hope it would be useful for you. So don't forget to leave a like, share the content, and subscribe to the channel. Keep the channel alive. I am trying my best, going out of my way, working midnights to keep the channel alive. So I need that kind of motivation from you. I know you love me, so but that love should be reciprocated in terms of just propagating the channel. Okay, so thanks a lot. See you in the next awesome video.